So there's very similar other effects about differences in dimension, the difference between, say, surface area and volume. And I want to talk about some interesting mathematical examples now. And one of those examples is the paradox of Gabriel's horn. So Gabriel's horn, so we look at the function of 1 over x. So this is y equal 1 over x. And we start at the point 1. We're just going to look at this part of the curve here. So it goes all the way out to infinity. So, and to form Gabriel's horn, we take that line and we revolve it around the x-axis. So we make a kind of symmetric kind of shape like this. Yeah, and it's kind of like a horn from heaven. Maybe we can imagine it with a sonorous tone, maybe this multi-tone coming from heaven. And this is why it's called Gabriel's horn. Yeah. So Gabriel's horn is obtained by revolving this function around the x-axis and making this kind of surface. So I could put my arm in, it's sort of like a horn. Okay, so now the paradox of Gabriel's horn is the following observation. Well, I want to ask, what is the volume of Gabriel's horn? Yes, I mean, it's an infinite object because it keeps going forever, but it's 1 over x, and so it's very thin out there when you go very far. And so we can compute the volume of this. And in order to compute the volume of this, well, it's a kind of standard problem in calculus to compute the volume of a surface of revolution. And the way that you do it is in the typical calculus manner. You imagine sort of slicing it into cross sections. So we're going to slice this horn into these kind of discs. Yeah, I'm thinking of the solid, the volume of the solid, the part inside the horn as well. That's what I'm talking about. And if I slice it like this, then if I'm at point x here, the radius of that disc is 1 over x, because that's the function that we're rotating, yes? And maybe the thickness, if you know how to do this, is dx, the infinitesimal dx, yeah? So the volume of one disk is the area of that disk times the thickness, but the area is pi r squared, so therefore the volume of one disk is pi times 1 over x squared dx. So that's the area times the thickness, yeah? So the total volume will be the integral from 1 to infinity of the volume of each disk. Yeah? So we took the whole thing, we slice it into these disks, we calculate the volume of each disk, that's the integrand, and now we're going to add them up. That's exactly what integration does. So this is equal to the integral from 1 to infinity of pi over x squared dx. Okay, but I can compute this integral. This is an elementary calculus integral. The integral of 1 over x squared is minus 1 over x. So we have here minus pi over x from 1 to infinity. And when I put in infinity in for x, the limit will be 0. So it's 0 minus, using the fundamental theorem, the value when I put 1 in. But there's a minus sign here. So it's minus pi over 1. And so I get pi. So the volume of Gabriel's horn is precisely pi, which is a finite number. That's the first paradoxical part about Gabriel's horn. It's an infinite object, but it has a finite volume, pi. So the volume of Gabriel's horn is finite. Okay, that's nice. But the second part of the paradox is to ask, what is the surface area of Gabriel's horn? Yes. So now instead of asking the volume, I want to ask the surface area. Well, for the surface area, we don't want the volume of this disk, but rather we want to concentrate on this band on the outside, which, if you think about it, is what's called the frustrum of a cone. It's slightly angled, right? And the angular piece here is commonly called ds, which is the square root of dx squared plus dy squared. And I can think of that as, if I factor out a dx, 1 plus dy dx squared dx here. So the length, the infinitesimal length of the frustum part is this square root times dx. So the total surface area will be the integral from 1 to infinity of the surface of one frustum, but that's the width of that frustum times the circumference, and the circumference is pi times the diameter, so that would be 2 pi over x. So we have 2 pi over x times this square root thing, 1 plus dy dx squared dx. And dy dx squared, well, y was 1 over x, which is like x to the minus 1, and so dy dx is minus 1 over x squared, and so this turns into 1 over x to the 4th. Okay, so this is more complicated, but one can calculate. In fact, we can just ignore this square root. It's always at least 1, so this is bigger than or equal to the integral from 1 to infinity of 2 pi over x dx. If I just observe, this is at least 1. So this whole thing is at least as big as this. And this is 2 pi log x from 1 to infinity, which is infinity. Okay. So the point I'm trying to make here is that the surface area of Gabriel's horn is infinite, but the volume of Gabriel's horn is finite. Okay. The surface area is infinite and the volume is finite. But how could that be? I mean, can't we just fill it with paint? Suppose I point it down and I just fill it with paint. It has a finite volume. So with finitely many buckets of paint, I can fill it up. And that paint would be touching every part of the surface. So with a finite amount of paint, I can paint Gabriel's horn, right? So that's the kind of puzzle of the paradox of Gabriel's horn, is that it's a geometrical object that we can understand in a deep way, and yet it has finite volume and infinite surface area. Okay. And so, what about this filling with paint idea? I mean, does it really work? Does it convince you, if you have an object, a container, and you fill it with paint, then would it ever take more paint than that to paint that surface? And I would say, well, actually, we're cheating a little bit with that argument, because the Gabriel's horn is getting thinner and thinner as you go out here. And so the paint that's inside Gabriel's horn was spread very thinly when you go very far out. If you say, well, to paint a surface, there should be a uniform 1 millimeter thickness of paint on it, then eventually we weren't obeying that 1 millimeter thickness, because the horn itself was less than 1 millimeter across. And so even though the horn was full of paint, it doesn't mean that we've painted to a uniform thickness. Yes. And so that's a way of seeing, well, look, just filling Gabriel's horn with paint shouldn't count as painting the surface, because you've spread the paint so thin in the part that's way out there. But the part that's way out there is adding to the infinite surface area. Most of the area is out on the tail, because if I chop it off, then what remains here is obviously just a finite area. So it's totally cheating to try to paint the surface by filling the volume with paint, because the paint will in effect be spread so thinly.